Thank you, Dr. Binoy Jacob, for inviting me to give a talk on the unity of science and humanities, a mathematical perspective. Unity of science and humanities, a mathematical perspective. Traditionally, there is a split between science and humanities, in the sense that while science is mathematical or at least mathematizable, humanities are considered non-mathematical. A preliminary attempt is herein made to bridge this chasm by highlighting the existence of several parallels between logic, which is used in humanities as well as in science, on the one hand, and set theory, which forms the basis of mathematics, on the other. Both logic and set theory are shown to be representations of an abstract formalism called LS theory, which unifies all knowledge. Well, what I want to start with is to tell you that traditionally we have regarded science and humanities as impenetrable compartments. This gulf should be bridged because there are several parallels between logic, which is primarily used in humanities, as well, and set theory, which forms the basis of mathematics. Both logic and set theory can be shown to be representations of an abstract formalism, which we call LS theory, which unifies all knowledge. What the significance of LS is, I will explain as we go along. Next, logic has been hailed as the science of reasoning and set theory as providing a foundation for mathematics. In fact, logic finds application not only in mathematics, but in every other discipline as well. This has prompted a group of mathematical philosophers such as Frege, Russell, and Whitehead to claim that the whole of the propositions of mathematics to be reduced to certain fundamental notions of logic. In this talk, we propose to examine the question of unifying logic and set theory, at least at a finite level. We will argue that logic and set theory are representations of some abstract algebra. Well, abstract algebra is an abstract structure, mathematical structure. Its elements may be different things. For example, our ordinary arithmetic is an abstract algebra. Its elements are numbers, ordinary numbers. Several operations can be defined for numbers and so on. But they are representations of some underlying algebra. Next. It was Aristotle who, in the 4th century BC, laid the foundation of logic that came to be known as Aristotelian logic or classical logic. For the next 2000 years, no significant developments took place in the subject. The proposal for a revised version of logic, called the universal calculus of reasoning, was made by the great mathematician and philosopher Leibniz in the 17th century. 2 centuries later, George Boole, an English mathematician, published the work The Laws of Thought, in which he applied his class algebra to several branches of logic, including Aristotelian logic. Several distinguished names appear in the list of logicians or mathematicians who contributed to what came to be known as symbolic logic or mathematical logic. These include De Morgan, Jevons, Peirce, Frege, Peano, Russell, and Whitehead. The last pair co-author the masterly classic Principia Mathematica. Well, I have summarized the history of development of logic from starting with Aristotle in the 4th century BC. He laid down the fundamentals of what is today known as Aristotelian logic. It is of limited scope. For the next 2000 years, there were no important applications or developments. Then the first development took place in the 17th century when Leibniz, the great mathematician and philosopher, formulated a calculus of reasoning, universal calculus of reasoning. Then 2 centuries passed by, and in 19th century, George Boole, an English mathematician, published a remarkable work, namely The Laws of Thought, which guided the development of mathematical logic in the same century. The notable people who contributed to mathematical logic in the 19th century are De Morgan, Jevons, Peirce, Frege, Pino, Russell, and Whitehead. The last pair co-authoring the masterly classic, namely Principia Mathematica. Over to the next. The term class or set was widely used in the 19th century by logicians in the sense of collection. But the first mathematical theory of sets was the creation of just one person, namely Cantor, as part of his attempts to understand infinity. Russell was amazed when he discovered paradoxes in the Cantorian theory of infinite sets. The thesis that mathematics is reducible to logic is called logicism. Not all mathematicians subscribe to this opinion. To avoid paradoxes, we will be dealing only with logic of finite propositions or statements and finite sets. Our presentation will lead to the demonstration that logic and set theory in their finite editions run parallel. The two approaches are united in the sense that they define different representations of an algebra called the LS algebra. Some implications of this result will also be mentioned. Okay, here in the previous slide as well as the present one, we have discussed the historical setting for the theory called mathematical logic and set theory. There are several versions of set theory, but we will be presenting only the simplest and simplest version called the naive set theory launched by Cantor. It has some complications, but we'll not tread the complicated terrain. Our dealings will be only with finite sets and logic of finite propositions. Of course, the infinite sets and infinitely long propositions are definitely more interesting from a mathematical point of view. However, we don't discuss these things here. So our approach is again presented here. Once again, we make a twofold attack on the question of unity of science and humanities. From one angle, namely logic, we approach knowledge. Knowledge means science and the union of science and humanities. We approach that union, that unified thing from the angle of logic. From the other angle, namely set theory, we will be making another approach. These two, we shall find that they are different representations of the same set of basic rules. The basic raw material in logic is propositions or statements. So I'm going to explain what a proposition is by means of examples. India is a tropical country. It's a statement. Another statement, children of underprivileged classes in India find it extremely difficult to cope with online classes. The sum of the angles of a triangle is 2 right angles. Jawaharlal Nehru is the father of our nation. We have considered 5 examples. Questions exclamations and the like are excluded from the class of propositions. None of these will be considered as propositions. So by proposition we mean a statement. Lowercase letters P, Q, R, S will be used to denote propositions. Over to the next slide. It is the sense of a proposition that is important, and not the language in which it is stated or the style employed in expressing it. This is a very important sentence in the whole talk. I said a proposition is a statement, just a statement, but it is the meaning or essence of that statement which matters. You may state it in English or Malayalam or Hindi or any other language. The presentations will be different, but the idea will be the same. So it is the idea that we focus on, and it is the idea which we call a proposition. So it is sufficiently abstract right at the beginning. Even the very concept of a proposition is abstract. I hope you appreciate this idea. A proposition has a truth value. So this is another point. A proposition has a truth value which indicates whether it is true or false. If a proposition is true, its truth value is T, capital T. And if it is false, its truth value is capital F. In the examples given above, all but the last one are true propositions. The false proposition is the fifth. Say, we will be stating a proposition. We have to present a proposition, represent a proposition in a certain language. And that requires the use of certain constants. These are called logical constants, or loosely called connectives. I will come across these and we will explain them using examples. A truth value is used to define the effect of an operation on one or many propositions. So every proposition has a truth value. It may be true or false. If you apply the certain operations, you will produce new propositions from a given set of propositions. That will have another truth value, which may be different from the truth values of the component propositions, and so on. The fundamental operations of this kind are negation, conjunction, disjunction, or inclusive or, disjunction, exclusive or implication, conditional, and by implication, or logical equivalence. The operations and the corresponding truth tables are given below. So I have introduced the number of operations, starting with negation. Negation means you are stating a proposition, and by negation operation, we are producing a proposition whose truth value is just the opposite. Next slide. The example, tomorrow is a holiday. The negated form is tomorrow is not a holiday, P bar. The operation is defined by this table, small table. P and P bar are given. If the proposition is T has a truth value Q, then the proposition P bar has a truth value F, namely false, and vice versa. Next, please. Conjunction. Conjunction is, as the term suggests, is joining. P and Q are two propositions. In the third column, the truth value of the conjoined or conjuncted pair is given. For example, if P has a truth value T and Q truth value T, then P conjunct Q is a true proposition, and so on. Next, disjunction. The two propositions P and Q, they are disjointed. I have given examples there. Disjunction or inclusive or means either or both. P and Q are two propositions. Then P disjuncted Q as truth value determined by the third column. Next, disjunction exclusive or either or not both. Given two propositions P, Q, then the exclusive or is defined by the third column. Next, conditional or implication. So, conditional is represented by the logical constant if then. If P, then Q. If P is true, then Q is true. Like that. So the several cases are shown there in the table. For example, if a proposition P, we are back on the table defining implication or conditional. The arrow denotes implication. Let us take the second line, T. Under P, you have got T, and under Q, we have got F. Then the truth value of P arrow Q is F. That means a true proposition implying a false proposition, that is false. The result will be false. That's the meaning. A true proposition implying another true proposition, that is indicated by the first line, that is true. Similarly to other cases. Next, please. Biconditional. That means P implies Q and Q implies P. Then P and Q are equivalent, logically equivalent. It's a case called by implication. Implication both ways. Next, please. Truth table for by implication. Next, please. We pass on to another aspect of the presentation, namely algebra of propositions. Of course, this algebra is already implicitly given by the truth tables, but this is another way of presenting the same rules. For we are hard pressed for time, so I'll be quickly passing through some of these slides. Say, for example, the algebra of propositions. The first one, identity. P, that is a conjunction, P conjunct T. That means a proposition P is conjuncted with another proposition which is true. Or a proposition which is false is conjuncted with another true proposition. Then the result will be the same as the truth value of P. That is the meaning of this highly cryptic formula. I don't have time to explain all this. Of course, later on, all these will become available in the YouTube, and then you will have no problem in deciphering some of these things. Next, please. The other rules of this algebra, idempotency, commutativity, and associativity. These are, some of these are already known to you from arithmetic. Commutativity, for example, P or Q is the same as Q or P. So they are logically equivalent. Similarly, P and Q is equivalent to Q and P. The order doesn't matter. Similarly, associativity. The next, distributivity. Distributivity, both operations are involved. P or Q and R is equivalent to, logically equivalent to P or Q and P or R. Similarly, the next line, De Morgan's law. So we are passing from one set of propositions, two propositions PQ to their negations, P bar, Q bar. They are joined by the two operations. What happens? Next. Now, this is all I can devote. This is the only this much time only I can devote to presentation of the essentials of logic. Now, set theory. Set theory is more familiar to those who have studied mathematics at school, high school. The last line, the building blocks in set theory are sets. They are the objects. A set is a collection of objects with some specified property. The objects are called its elements or members. A set may be represented by listing all its members or by specifying a role or membership. For example, Z equals 1, 2, etc. N is the set of positive integers. Z may be alternatively defined by Z equals set of X, where X is a positive integer. X stands for, X is a logical variable. It stands for a positive integer. Next, please. Algebra sets. Here, there are two operations, union and intersection. These are analogous to the operations we considered in logic. They are defined. Those who already know these things can skip these things. A union B is the set of all elements of A or B or both. A intersection B is defined as elements, set of all elements of A and B that are common to both. The set of all sets of the specified type under discussion is called the universe X. It is from the universe that we pick particular sets. The null set or empty set is a universal set containing no elements. The concept of subset, A is contained in B. If A is contained in B, it may turn out that A is a proper subset of B, or A is just B. A is the same as B. So these cases are introduced here. Null set, phi is a unique set. Null set has no elements. It is just an abstraction. It is like the vacuum of physics. It is an abstraction. We know that there is nothing called vacuum in the universe. There will be some fluctuations at least. But here, mathematical vacuum, the null set is without any elements. Next, I consider the algebra of sets, identity, idempotency, complementation. Next, double complementation, commutativity, analogous to the commutativity we considered in logic, associativity. Next, distributivity, De Morgan's law. All these laws sound familiar because we have already had an exposure with similar things in logic. Next. Now we come to the last part of this talk, namely correspondence between logic and set theory. We have not stated any theorems. We have not given any proofs of anything. This is a very, very elementary presentation. It is just an exercise for the beginner who has already had some exposure to at least to set theory at school. I apologize to those of you for whom all this is quite strange, because we can't help for want of time. So we have presented two algebras, namely the algebra of propositions and algebra of sets. They are similar. That is our observation. The standard way to connect the two theories is through what is called quantification. I don't explain it here. We are going to follow a different route, which is simpler. That also leads to the same result. A set A that is defined on the basis of a property P allows one to associate with it the proposition that defines P. Thus, we may write A is the set of all X such that X has the property P. X here represents any element of X. X is a logical variable. This equation may be understood as a connection between the proposition defining P or simply P and A. A is called the truth set of P. So we have a proposition P, which is just a statement, and that statement we use as the property that in order to define a set. Here the meaning is that the set A contains objects which have the property P. It is called the truth set of P. Next. The set of all elements having property P is unique, but it can have many subsets, all of which obey the algebra of sets. Thus, there is no one-to-one correspondence between properties or propositions and sets. It is a one-to-many relation, but another interpretation is also possible. See, we have tried to connect a proposition with its truth set. The truth set is the set of objects having the property P. Set of the truth set consists of sets. So we started with the proposition and we end up with a set of sets. Therefore, there is no one-to-one correspondence between the two. On the other hand, we are introducing a new idea here. Instead of this, in order to connect set theory with logic, we follow the following convention. If a set is non-empty, that means if a set contains objects, then the proposition corresponding to it is true. So we assign a truth value to a set and call it T if A is non-empty, and a truth value F if A is empty. This is just a convention, and you can check that set theory goes over smoothly into logic with this assignment of truth values. This might sound a little magical, but there is no magic in it. We have simply assumed that a set can be assigned a truth value, and then that set is called a proposition. It is a convention. If the set is non-empty, then the truth value is T, and if it is empty, then the truth value is F. Next, we have considered propositions and sets, two departments. Propositions are characterized abstractly by essence or meaning, not the language. Then we consider operations for both propositions and sets. They run parallel. So in general, we imagine that there is an algebra of abstract elements. That is what we call the LS algebra or L. You can take its representation as logic. Then you will be talking about propositions. If you take S as set theory, then you will be talking about sets. So symbolically, we introduce three operations, and these are to be defined properly as the set, as the occasion demands. So, to sum up, logic is the framework of mathematics, but has been employed as a tool for argumentation in other disciplines also. Set theory provides the official foundation of mathematics and logic. It is an organizing principle for other subjects, including science and humanities. The unity of science, logic, and set theory implies the unity of all disciplines and hence of all knowledge. Set theory represents nature. Then it also represents mathematics. As Galileo said, the book of nature is written in mathematics, in the language of mathematics. When we say the book nature is written in the language of sets, we are simply echoing what Galileo said. Then the logic is the science of reasoning. It is used not only in mathematics, but in other disciplines also. Very, very interesting connection between logic and set theory. It is not a novel observation at all. After writing these slides, I happened to read Bertrand Russell's Principles of Mathematics, chapter 2. There he refers to the same fact. He refers to some work done by a mathematician called Schroeder in the 19th century. He called this by duality between logic and set theory. Duality. Unfortunately, Bertrand Russell is not very much for this duality. He quotes an example showing that while the distributivity works for propositions, it may fail for sets. He gives an example. Unfortunately, I cannot go into the details now. That example, we can explain what is wrong with his example. His example contains a word, or, but that proposition is okay even without that word. So it is that word which upsets duality between logic and set theory as far as that example is concerned. So what is the lesson that we should draw? Set theory and logic are exact, they are dual representations of the same algebra. That is an exact symmetry, to use the language of particle physics with which many of us are familiar. This is a kind of symmetry, duality. You have logic and set theory. But that symmetry is broken by language. Language is a human construction, artificial construction. So we don't know when we upset the natural equivalence between logic and set theory, the natural duality between these two compartments of knowledge. So Russell gives is from English. There may not be the same example in Malayalam. Of course, the whole issue requires careful study, which after writing these slides, I have come across several interesting observations following from this identity or this symmetry. With one observation is that symmetry is broken by language. With these words, let me conclude. I have taken more time than I had actually planned, but the subject is so dry, and I apologize everyone for making such an uninteresting presentation of a subject with which to which I cannot do any justice in a lecture lasting half an hour or 40 minutes. Thank you. Thank you. Now the floor is open for discussion.
Thank you, Dr. Babu Joseph, for your scholarly presentation. Well, you have very brilliantly articulated the unity of science and humanities from a mathematical perspective with a specific reference to set theory and logic. Thank you so much. And I think you have set the platform for discussion. You have already indicated several other areas where researches and explorations could be done in future. I think it is fruitful to deal with some of the topics. So I request the participants to unmute and enter into discussion with the resource person. Your comments, suggestions, questions, everything is welcome, but kindly make sure that things are brief. Thank you so much. The floor is open for discussion.
It's a very good beginning, and also in relation to the series we are considering. One, of course, is it's a good simple exposition to the duality between logic and the basis of mathematics. It implies that mathematics should be applicable to other branches of logic. And logic is everywhere, almost everywhere, let's say, except where it fails, which is probably in poetry, which is probably in painting, which is probably in other areas. So in a way, mathematics has a role in many areas of human investigation. But the point is well taken. This is where I would like to make an observation regarding our educational system. Actually, it is very rigid, actually, in India especially. I remember, even today, most of you know about Edward Witten. He is a foremost physicist. He is the most brilliant physicist alive today, who is a top string theorist. But how many of us know that he started, I mean, his undergraduation was in history. And he did some political work for the Democratic candidate that time. And then switched over to applied mathematics. And then got interested in quantum field theory. And now he is the top string theorist. In fact, he got a Nobel, Fields Medal. One of the, I think, the only physicists to have got a Fields Medal. So this sort of flexibility is not there in our curriculum. If somebody starts with history, he's stuck with history. And this is, I suppose, it is basically because of traditional attachment to caste system. See, in caste system, if you are born to a particular caste, you can't move out of it. Therefore, I think a historian should move over to mathematics, and mathematics can move over to music. that flexibility is not there, and I hope the new educational policy, which probably is coming through, it's already come, should I think this is where we should concentrate on. Second thing is about, of course, logic. One lesson we all can learn from this initial exposure to logic and set theory is that these are important rather than memorizing things. And actually memorization and what do you call it, just learning by heart has become. And in fact, the great Fields medalist Manjul Bhargava has mentioned that in one of the lectures he gave in Bangalore, that we should go into problem solving, we should go into understanding than in learning. I hope this series will pave the way for that. And one more observation. We have a very brilliant, I mentioned about Britain, we have our own D.D. Kosambi, who was a historian. But before that, he was a mathematician. So I think we should allow at least the new, I didn't have that flexibility, but at least the new students have that flexibility. If to go for medicine, let them also learn mathematics. You'll only, all these branches of knowledge can enrich each other. Ideas are not confined to subjects. Ideas are a flow from area to another area. And that is what is lacking in our academic system, in our learning methods, in our even thinking methods. So I suppose for this lecture, and I'm very happy that this focuses on interdisciplinary exploration. But here there's a danger, I must say. One should be good at least in one discipline. Better you can be good at in two disciplines. But if you are not good at any discipline and you have you are trying to distribute your superficial knowledge about cliches from different, like in quantum physics, little quantum physics, and you are trying to put it in Advaita, in philosophy and things like that, or in medicine. That is not advisable. That is not desirable. So I think we should respect each discipline, and the learning should be to understand things. And every student and every researcher should go deep into what he's doing at that time, but should be open to ideas from other areas. And I suppose in our series of lectures, I have many things to say about this. On some other occasion, in fact, we should discuss these things. And this has been a very, very, very good initiative. And I hope other lectures also, others from different areas should come and contribute and think together. They can think differently, but they can think together too. They can influence each other. We all should influence. The idea is a set of many cultures, religions, colors, eating habits, and whatnot. That's how learning is, and that's how knowledge is. And wish you all the very best. Thank you, Dr. Babu. Thank you.
Thank you. There's not a question at all. So answer is active. I appreciate your views, and what you said is quite appropriate to the occasion. I have started the ball rolling. We wish that most of the talks will have an interdisciplinary flair. And you may start from your field of specialization, but please show how it is relevant to other disciplines or to knowledge in general. That is the aim of this series of lectures. It is different from online lectures usually marketed for students. This is for everyone. These lectures are for intelligentsia, who are members of the intelligentsia, who are interested in knowing about things with which they have very little familiarity. Thank you. Any other question? Any specific questions?
Dr. Babu Joseph, I see a message from one of the participants, Dr. Nina Joseph. Shall I propose that question?
Yeah.
Can we mathematize everything? How can we ever solve the disruption brought in by the language? Can we mathematize language? Can science capture nuances of emotions? Is there a limit to quantification? Well, many questions. You are free to address one or two. Thank you, sir.
Whereas the time available is very limited, so I'll address only one of the questions. We have discussed the unity between the duality between logic and set theory. And I have pointed out that there are instances in which language breaks this duality. The fault is on the part of language. So we have to refine our language. That is because logic and set theory, that relationship is fundamental. Language is an evolving thing. It goes on evolving. So what is considered grammatically correct today may be considered wrong tomorrow, and so on. Usages come, the phrases appear from time to time. Constructions appear from time to time. So language is developing, it goes on developing, whereas rules of set theory and logic are fundamental and they don't change. So we have to decide whether we should have something permanent, just like the logical structure. We can consider mathematics and logic to be essentially the same. In fact, that philosophy is called the logicism. Logicism. Both Bertrand Russell and Alfred Whitehead were pioneers in that school of philosophy. They said that mathematics is nothing but logic. I have considered an example of how set theory can be converted into logic by assignment of truth values to sets. So that is a simple, trivial thing only, but it goes deep. Therefore, my personal view is that we should consider this as a fundamental result, namely duality, and polish language in order that it may respect this duality. If there are no other questions, shall we wind up, Dr. Binoy?
Can you hear me, sir?
Yeah, yes.
I am Varadarajan from SH College, retired from. And you're talking about logic, which can be attributed to brain, its structure. So it differs from person to person. So how this will be different for different persons. So a lot of study should be the brain, and if you can find the logic of different, in a situation different people behave differently, take it differently. So how this connection helps us to contribute anything to the good of the society or some such thing?
You said about the diversity of functioning of brains of different people. But the basic principles of functioning are the same. Set theory and logic are basic principles. You might have noticed that there is a constant structure. For example, we introduce certain operations. It depends on what kind of propositions that you employ for arriving at conclusions. In logic, in Aristotelian logic, they are called premises. Different people employ different sets of premises, and that is why they arrive at different conclusions. It is not the fault of the logic. They always, every one of them uses the same method of logic, but the starting point can be different. That is why they diverge in different directions. Of course, as you suggested, a lot of study is required, but I think artificial intelligence, AI, they have studied the functioning of neural networks. Artificial simulations of neural networks are used in artificial intelligence. It is known today that the network, actual neural network, respects the rules of logic. The way signals move here in one direction or another direction, they move here and there. It is in accord with the principles of logic. So the brain respects ordinary logic, but the premises represented by the signals, electrical signals, the combinations and permutations and combinations of different nerve cells firing in different patterns make the difference at all.
Maybe some mathematical say modeling can be done, or does it obey laws of probabilities? Like if I am sad, can you quantify my sadness with respect to the amount of hormones that is secreted or the neural network? So is it possible, sir?
Yes, probability enters the picture. The network is not, even though it is deterministic, it is chaotic. The probability has a role to play in the activity of the brain. Ideas, formation of ideas, formation of conclusions, etc. These are governed by probability because the whole brain show is chaotic.
What about the ethics?
Pardon?
Ethics.
Ethics, yeah, it also follows logic. I said ethics is a branch of knowledge where which is modeled on the principles of logic. Therefore, it can be mathematized. In fact, Spinoza developed an axiomatic approach to ethics, similar to Euclidean geometry. I don't know the details. I have only heard from other people that Spinoza actually did it.
Okay. I think there are a couple of questions, Dr. Babu Joseph. Some of them have been messaged. I see a question from Dr. Kuruvilla Pandikata, but I am also seeing him online. So I would request Kuruvilla to propose the question direct.
Professor Babu Joseph, I am immensely grateful to you for your active interest, especially in bringing physics, philosophy, and now humanities together. Thank you for your great contribution. My only question is, in this age of specialization and compartmentalization, it is rather easy for people like you who have specialized in science to approach history or liberal arts. But it will be very difficult for those who have specialized, say, in humanities and liberal arts, to learn mathematics and set theory and this Boolean algebra. What do you say to that?
I think it is the result of conditioning, which takes place in our childhood. It is the result of the kind of school education that we have received. We have to go beyond it. In fact, many people say that there is not much to learn from school or college. 90% of your learning must be done outside. So don't follow the teachers, don't follow the syllabus. That's all what we can say. regarding this problem. If you, those of you who venture to go beyond the syllabus, beyond the advice of teachers and mentors, will see new territories. That is an experience shared by many people.
Thank you very much.
Okay.
We have probably the second last question by Dr. Joe Jacob. Joe Jacob, welcome.
Hello, sir.
Hello.
Yeah, I have a simple question, like maybe when I was having a dialogue with one of my colleagues in social science, particularly in the field of political science, we used to have discourses, and at times he tells me, or he confronts me, telling that, okay, Joe, in your science it is 2 + 2 is always 4. But for us in political science, you cannot judge me like that. There can be different tints of logic, or maybe the truth itself may not be that absolute. So you cannot judge it in that way. So I just wanted to get your comment on this. Since we are talking about logicalizing or mathematizing even social sciences, and your talk had been very useful, and I got many ideas in a new field. Thank you for that. And can you please comment on this? Because then I can confront him. Okay. Thank you, sir.
Many people believe that logic is not unique. Every man or woman has their own logic. Because like morality, there are people who consider morality to be relative. Those who claim that logic is relative, I think I will put them in the same category as the relativist philosophy or ethics. There is what is called fuzzy logic. Fuzzy logic, the truth value is a spectrum of values. A proposition need not be fully true. Its truth value, degree of truth may be less than 1. So you can have a variety of truth values. Similarly, falsehood, a proposition need not be absolutely false. I think it is a fuzzy logic that politicians are trying to inject into our heads. But nature respects standard logic at the macro level. At the micro level, quantum level, you know that the logic is totally different. Quantum logic is different from mathematical logic. So that is another terrain. So there are different possibilities, not only for those possibilities which have been pointed out by politicians, but by quantum physicists also. There are possibilities, immense possibilities. Okay, I don't know whether I have made myself clear.
Yeah, okay.
So, you want to ask another question, supplementary?
No, sir. Thank you. Thank you.
Anyway, it's interesting that a quantum physicist addressing the question from an astronomer, and both of them are talking about social science, Good. Appreciate it. And maybe one more question, as we are running short of time. As there is time constraint, we'll restrict to one more.
Father, I just make a comment about the Pandikats.
Please.
Hello, Father, can you hear me?
I can hear and continue, sir. Kindly proceed.
Father Pandikat raised the issue of social sciences and humanities, people from humanities learning mathematics. I can give you the example of Herbert Simon, who is a Nobel laureate. The first one, I think, probably amongst the first few of the economics prize. And he started out as a political scientist. In fact, his PhD was in political science. If you remember right, it was from Chicago University. Then he learned mathematics on his own. Went over to mathematical sociology, went over to management science, and finally he ended up with artificial intelligence. And he's a well-respected a leader in what he called polymath thinking. So I think all social scientists are welcome. The problem is teaching mathematics. So Father Binoy, people like you should teach them in a more simple manner to people who are outside the field.
Okay.
That is a solution.
Thank you. I think we are winding up. A word of gratitude to everyone. First and foremost to Dr. K. Babu Joseph for his very scholarly presentation. It was a brilliant exposition, affirming and confirming the interdisciplinary paradigm for the contemporary times, bridging mathematics, logic, and humanities. Thank you so much, Dr. K. Babu Joseph, for your wonderful exposition this evening. Thank you.